In a dusty corner of a university archive, a box of old film canisters sat untouched for decades. These were not just any old films. They were the forgotten work of a brilliant but eccentric zoologist from the 1960s. He was obsessed with a single, seemingly simple question: how does a hedgehog work? He believed the answer was not just in biology, but in physics. His notes, filled with complex equations, hand-drawn diagrams, hinted at a world of hidden mechanics. He saw the hedgehog not just as an animal, but as a marvel of natural engineering. His research was dismissed at the time, considered too strange, too focused on mathematics. But today, we are reopening his investigation. These old films show something extraordinary. Grainy black and white footage reveals a hedgehog in a laboratory setting. It is surrounded by strange contraptions, wires, measuring devices. The scientist's voice, preserved on a crackling audio reel, speaks with urgent excitement. He describes forces, pressures, energy transformations that are happening within this tiny creature. He saw the curl of its body not as a simple defense, but as a complex, biomechanical event. He measured the strength of its spines, the efficiency of its movement, and the physics of its famous roll. It's a glimpse into a scientific mind that was far ahead of its time. A mind that understood that nature's secrets are often written in the language of numbers. This forgotten archive is our starting point. It's a treasure map leading us toward a deeper understanding of one of the world's most beloved animals. The central question that drove this scientist, and now drives us, is profound. How do hedgehogs harness the fundamental laws of physics to survive and thrive in their environment? How does this small mammal, seemingly so unassuming, perform such incredible feats of engineering every single day? It is a question that takes us beyond simple observation and into the very mechanics of life itself. The answers are hidden in plain sight, in the curl of a spine and the shuffle of a foot. We will follow the clues left behind in these old notes, films. We will bring modern technology to bear on these decades-old questions. We will recreate his experiments using high-speed cameras, advanced sensors, and computer models to reveal what he could only theorize about. This journey is not just about the hedgehog. It is about a way of seeing the natural world, where every living thing is a master of physics, a product of millions of years of research and development. This documentary will unlock the secrets hidden within the hedgehog's spiny armor, revealing the beautiful and complex physics that make this animal a true survivor. The hedgehog appears to be a very simple creature. It snuffles through our gardens at night, a small, prickly ball of life. We see it and we might think we understand it, but its true nature is hidden. It communicates in a language we rarely try to understand. This is not a language of sounds. This is a language of physics. This is a language of biomechanics. Every movement, every defense, every interaction with its world is a carefully calculated equation. The arrangement of its spines is a lesson in force distribution. The way it rolls into a ball is a masterclass in leverage and in potential energy. This is the secret language we are here to decipher. To understand this language, we must look closer. We must move beyond the charming exterior and examine the machinery within. Imagine you could see the forces at play when a predator attacks. The impact is not met with simple brute strength, but with an intricate system of shock-absorbing spines that spread the force, protecting the delicate body inside. Each spine is a tiny cantilever beam, engineered to bend but not break. The complete system of 5,000 to 7,000 spines works in unison, a living shield that is strong and lightweight. This is not just biology, it is sophisticated material science and structural engineering. The physics doesn't stop with defense. Consider the simple act of a hedgehog walking. It seems like a slow, shuffling gait, but high-speed footage reveals a surprisingly efficient form of locomotion. We can analyze its stride, the timing of its footfalls, and the forces it exerts on the ground. We can calculate the mechanical work it does with every step, and understand how it conserves energy on its nightly foraging trips, which can cover several kilometers. This is the science of biomechanics. It shows us that the hedgehog is an economical runner, finely tuned to its environment and its needs. It is a world of detail invisible to the naked eye. Our mission is to make this invisible world visible. We will use the power of science and mathematics to translate the hedgehog's secret language for you. We will show you the numbers behind its survival. We will measure the forces, calculate the energies, model the mechanics. This isn't just a story about an animal. It's a story about the universal principles that govern all life. By the end of our journey, you will never look at a hedgehog the same way again. You will see it not just as a cute garden visitor, but as a true physics marvel, a testament to the elegant solutions that evolution can produce. To begin to understand the hedgehog as a machine, we must first look at its most obvious feature: its remarkable coat of spines. This is not fur. It is a dense covering of thousands of sharp, stiff quills. An adult European hedgehog can have between 5,000 and 7,000 of them. Each quill is a marvel of biological engineering. This spiny overcoat is the hedgehog's first line of defense, a visual warning to predators. It is a masterpiece of evolution, a simple, effective solution to survival. But to truly appreciate it, we must examine structure and material. These spines are made of keratin. The same protein makes up our hair, fingernails. Yet the hedgehog's spines differ in form and function. They are not solid. They are mostly hollow, with complex air-filled chambers. This makes them incredibly lightweight and surprisingly strong. Human engineers use the same principle. A hollow tube can be stronger than a solid rod of the same weight. The hedgehog mastered this millions of years ago, creating a protective shield that doesn't weigh it down. The hedgehog's shape is also crucial. A simple, rounded form, almost teardrop from above. This lets spines point outward in every direction when it curls. No weak points, no easy angles of attack. The body is compact and low to the ground, a low center of gravity. That stability underpins its famous defensive role. Its simple body plan is actually highly optimized for foraging and defending against threats from above. We are looking at a living fortress. The spines are its walls. Its rounded body is the keep. Unlike stone, this fortress is flexible, lightweight, and alive. It can move. It can feel. It can react in an instant. The story of the hedgehog's physics begins with this external anatomy, an anatomy that speaks of ingenious passive defense, a design that turns standing still into resilience, thanks to its spiny overcoat. Let us now isolate a single spine and examine it more closely. It is a beautiful object in its own right. It measures about 2 to 3 centimeters long, just a little shorter than a standard paperclip. At its base, it tapers to a tiny, flexible neck before swelling into a small ball that sits inside a follicle in the skin, much like a ball and socket joint. This clever design allows the spine to pivot in any direction. More importantly, it is designed to bend at the neck upon a severe impact, rather than being driven into the hedgehog's own body. It's a built-in safety mechanism, a tiny shock absorber at the root of every single quill. If we were to cut a spine in half and look at it under a microscope, as our pioneering scientists did decades ago, we would see its hidden genius. The outer wall is a thin, hard shell of keratin, but the inside is not empty. It is reinforced with delicate, paper-thin walls of keratin that run along its length. These are called septa. They divide the hollow interior into a series of small, air-filled pockets. This structure, known as a composite material, is incredibly strong for its weight. It prevents the spine from buckling or collapsing under pressure, much like the corrugated structure of cardboard makes a simple sheet of paper strong enough to build boxes. We can even measure the properties of these spines. Our archival notes show experiments where individual spines were compressed until they buckled. The the data reveals they can withstand a surprising amount of force. A single spine is stiff enough to deter a predator, yet flexible enough to bend without snapping. When you multiply this strength by 7,000, you begin to understand the formidable nature of the hedgehog's defense. It is a system built on the power of numbers. No single spine is invincible, but together they form a shield that is almost impenetrable to the teeth and claws of animals like foxes or badgers. This is material science at its finest. The hedgehog has evolved a material that is light, strong, and cheap to produce from a biological standpoint. Human engineers spend billions developing similar composite materials for aerospace and construction. We strive to create structures that are both lightweight and robust. The hedgehog has been manufacturing such a material for millions of years, covering its entire body with it. Each spine is not just a defensive point, it is a testament to the efficient and elegant solutions that nature can produce through the slow, patient process of natural selection. It is engineering on a miniature and truly masterful scale. The hedgehog's most famous behavior is its ability to roll into a tight ball. This is not a slow, deliberate action. It is a lightning-fast reflex, an almost instantaneous response to a perceived threat, a sudden noise, an unexpected touch, the shadow of a predator passing overhead. In less than a second, the vulnerable, soft-bellied animal transforms into an impenetrable sphere of spines. This is the hedgehog's ultimate defense, a biomechanical marvel. But how does it achieve this feat of natural origami? The process begins with this rapid, instinctual reflex action. The trigger is processed by the nervous system, sending an immediate signal to specialized muscles. The first movement is often a sharp, downward tuck of the head and the tail. By bringing extremities toward its core, it prepares the body to be folded. Simultaneously, the panniculus carnosus across the back begins to contract. The musculus orbicularis, the drawstring muscle, starts to tighten, a highly coordinated, pre-programmed muscular cascade, executed without conscious thought, pure, evolved instinct in motion. Even newborn hedgehogs, called hoglets, will attempt it. Their spines are soft and muscles weak. Attempts make a comical, partial curl, but the instinct is there from day one. As they grow and muscles strengthen, the curl becomes tighter and more effective. This shows the rolling reflex is not learned. It's hardwired into neural pathways. The cornerstone of the hedgehog's defensive strategy, life-saving and needing to be perfect from the first attempt. We can analyze this with high-speed cameras, even though archival work used limited equipment. Slow motion reveals the precise order of muscle contractions. We can see how the body's momentum is harnessed to aid the curl, and how the skeleton flexes to accommodate the tight fold. The act of curling is a beautiful demonstration of basic physics, specifically the principles of leverage and torque. As the hedgehog begins to roll, it uses its body as a system of levers. The musculus orbicularis, the circular drawstring muscle, is the primary engine. As it contracts, it pulls the edges of the spiny mantle. The muscle action generates a powerful turning force, torque, on the upper half. A modest force, well positioned, can produce significant torque, enough to overcome body weight and stiffness and fold it in half. As it curls, it pulls its head, legs, tail toward the center. Mass becomes concentrated into a much smaller, spherical volume. Physics: a spinning object spins faster as mass moves closer to the center. Not spinning like an ice skater, but the same principle helps the curl finish faster. This is conservation of angular momentum. Once the hedgehog has curled into a ball, the next crucial step is to lock this position. This is where the true power of the panniculus carnosus muscle comes into play. This contraction pulls the skin of the back incredibly taut. The effect is twofold. First, it ensures the ball is as tight as possible, leaving no gaps. Second, it causes all 7,000 spines to stand rigidly erect, pointing outwards in every direction. This locking mechanism is incredibly strong. Trying to uncurl a determined hedgehog is nearly impossible without harming it. The force exerted is immense and sustained. It is a state of maximum isometric contraction. This sustained effort can be maintained for hours if necessary, a testament to the endurance of these specialized muscles. The hedgehog effectively becomes a living fortress, and the muscles are the bolts that lock the gates shut, waiting for the danger to pass. When fully curled, the hedgehog achieves a near-perfect spherical shape. This shape is not an accident. It is geometrically the most effective defensive posture possible. A sphere has the smallest surface area for a given volume. No corners, no edges, no weak points. Every angle of attack is met with the same formidable defense. A dense array of sharp, outward-pointing spines. When a fox tries to bite, the force is met by the points of dozens of spines. According to the formula for pressure, pressure equals force divided by area. The incredibly small area of the spine tips means that even a small biting force creates an immense, painful pressure on the predator's mouth. This spiny sphere is also a brilliant shock absorber. The entire matrix of spines deforms slightly. This system works together to dissipate the energy of the impact. It is like a combination of a pincushion and a stress ball, both sharp and yielding at the same time. The spherical shape also makes the hedgehog difficult to manipulate. A predator cannot easily get a firm hold. If pushed, it simply rolls. This rolling motion can be a defense in itself, allowing the hedgehog to tumble away from danger. Once uncurled and on the move, the hedgehog reveals another side of its mechanical nature. Its typical movement is a distinctive shuffle or waddle. It seems slow, perhaps even clumsy, to our eyes. But we must be careful not to mistake this unique gait for inefficiency. The hedgehog is a nocturnal forager, and its locomotion is perfectly adapted for a life spent covering long distances in the dark, searching for food. It moves with what is known as a walking trot, where the diagonal legs move at roughly the same time. The front left leg and the rear right leg swing forward together, followed by the front right and rear left. This pattern provides constant support and stability, which is crucial for an animal that navigates the uneven terrain of the forest floor and garden undergrowth in near-total darkness. The rocking motion we observe is also a key part of its movement. As it lifts one diagonal pair of legs, its center of mass must shift over the supporting pair to maintain balance. This causes the characteristic side-to-side sway. A single night's journey for a hedgehog can be surprisingly long. Tracking studies have shown they can travel for 2 or even 3 kilometers, or well over a mile, in their search for slugs, worms, beetles. Their seemingly slow shuffle is, therefore, the walk of a marathon runner, not a sprinter. It is a gait that has been honed by evolution to be as energy efficient as possible over very long distances. Let's zoom in and analyze the mechanics of a single hedgehog footstep. High-speed cameras, force-sensitive plates. Let us see details our archival scientists could only have dreamed of. Plotting these forces over time creates a unique signature. Duty factor is the fraction of time a foot is on the ground during a stride cycle. A cheetah. Low duty factor. Hedgehog. High duty factor. Typically well above 1/2. It moves diagonal legs together, so at least 2 feet are on the ground at all times, ensuring maximum stability. From force data, we calculate mechanical work per step. Propulsive force does positive work, adds energy. Braking force does negative work, removes energy. The shuffle is more efficient than it looks. Forces are applied smoothly, no sharp peaks or jolts. This minimizes energy wasted starting and stopping the center of mass. A system tuned for economy. A hedgehog's locomotion is not just about getting from one place to another. Its movement is intricately linked with the act of finding food. Its walk is a stop-and-go pattern. When a hedgehog detects an earthworm or a beetle grub just below the surface, Its locomotion changes. It stops its forward shuffle and engages its powerful forelimbs. Its broad front paws, armed with strong claws, are not just for walking, they are digging tools. The hedgehog will plant its hind legs for stability and use its front paws in a rapid, alternating scratching motion. This foraging behavior demonstrates the versatility of the hedgehog's biomechanical design. Its body is a multi-tool. One of the greatest challenges for any small, warm-blooded animal is staying warm. Physics tells us that small objects have a larger surface area relative to their volume. This means they lose heat to their surroundings much more quickly than large objects. Its most powerful tool for surviving the cold is a process called hibernation. Its heart rate can drop from around 190 beats per minute to just 20. And most remarkably, it allows its core body temperature to plummet. By doing this, it drastically reduces the temperature difference between its body and the environment. By becoming cold, the hedgehog almost stops losing heat altogether, allowing it to survive for months on its stored fat reserves. The hedgehog navigates a world of smells, sounds, vibrations. It can feel subtle vibrations traveling through the soil, the burrowing of an earthworm, the scurrying of a beetle underground. When building its winter nest, the hedgehog becomes a tiny environmental engineer. The interlocking, randomly oriented leaves create a material that is surprisingly strong and an excellent thermal insulator. Perhaps the most bizarre and least understood behavior of the hedgehog is a strange ritual known as self-anointing. Throughout this journey, we have peeled back the layers of one of nature's most familiar yet misunderstood creatures. We have seen the hedgehog not just as a collection of cells, but as a beautifully integrated, functioning machine. Our exploration was made possible by a unique fusion of the old and the new. It began in a dusty archive, with the grainy films and yellowed notebooks of a scientist who was ahead of his time. We brought modern tools to bear on these decades-old questions. This combination of archival inspiration and modern technology allowed us to translate the hedgehog's secret language of physics. The numbers are the very heart of this story. By quantifying the forces, measuring the densities, and calculating the energies, we moved beyond mere appreciation to a deeper level of understanding. Understanding the hedgehog as a physics marvel brings with it a profound sense of responsibility. Hedgehog populations in many parts of the world are in steep decline. Its brilliant defenses are no match for the wheels of a car or the loss of a safe place to hibernate. Our newfound understanding gives us a unique insight into its conservation needs. Creating hedgehog highways, avoiding slug pellets, leaving wild, undisturbed corners in our gardens. The future of this tiny marvel of engineering is in our hands. Its survival depends on our willingness to make small changes in our environment to accommodate its needs. We hope this journey into the hidden world of the hedgehog has been as fascinating for you as it has been for us. We hope you will now see this familiar creature with new eyes. If you enjoyed this documentary and want more, please like this video. And to ensure you don't miss our next expedition into the archives of science, please subscribe to our channel. Thank you for watching.